In this video, we're going to look at an application of sound waves and how instruments create that sound wave, whether it is a string instrument or an air resonating instrument, how a standing wave is able to form different notes. So we'll talk about harmonics and the different frequencies that instruments can play. Now, instruments all are kind of built off of the back of standing waves. Almost every instrument that is playing a note is doing so with standing waves playing some kind of role. A standing wave doesn't actually look like this picture. It looks something like this, where an object or wave is oscillating between two different positions. We have some parts of this wave that it is not oscillating with any amplitude. We call those nodes, and some parts where it's oscillating a lot. Those are called antinodes. So this picture here is showing 6 different nodes and 5 different antinodes. Now we can think of this as like one long string. Let's say that this string or this giant slinky is 12 meters long, and we have four different standing wave configurations. We count the number of standing waves by the number of amplitude, uh, number of complete antinode setups we have. So we have one antinode followed by 2, then 3, then 4. So the number of standing waves are the number of antinodes. Or think of like if this were a jump rope, how many jump ropers jump individually in those different spots? The number of wavelengths is not looking at the number of standing waves, but looking at just one side of this. So this is showing the two different positions, but if there was a freeze frame, we would see just the red or just the blue. The blue goes from the equilibrium up to the peak, down to the trough, and back to equilibrium. That is one complete wavelength. If the total distance is 12 meters, the wavelength in meters is 12. We have one complete wave in 12 meters. One wavelength is 12 meters. Now we can look at this top one. There's one standing wave, but looking just at the blue, I go up to the peak and back down to the middle. That is not going down to the trough. That's only half a wavelength. If you have half a wavelength in 12 meters, you get a full wavelength, you need double that, or 24 meters total. You could also do this with some simple math and say 12 divided by 0.5 would give you that wavelength. If we jump all the way to the bottom, this 4 standing waves actually has 2 complete wavelengths, down to the bottom and back to the top, bottom back to the top, 2 wavelengths showing up there. That means 2 wavelengths, 2 waves fit in 12 meters, so each one is going to be 6 meters. 12 divided by 2 is 6. Now, you may have noticed a pattern. Every time we have a number of standing waves, if we cut it in half, that will give you the number of wavelengths. So 1 becomes 0.5, 2 becomes 1, 4 becomes 2, 3 becomes 1.5. It goes up and down and back. That's one wave, and then another half a wave. If I use this process of taking the total length divided by the number of wavelengths, 12 divided by 1.5 is 8. Another way that you can look at this picture, if it's 12 from end to end, it looks like it's split up into 3. You need 2 standing waves for one wavelength. So it's essentially 2/3 of the total 12. 2/3 of 12 is 8. All right, strings can make sound. Here's a little ukulele. This string is vibrating back and forth, and it's vibrating back and forth, making a standing wave. So the standing wave, I've got uh, a node up here and a node down here, and it oscillates with an amplitude in the middle. There are a couple different things that I can do. If you have a string instrument, one way that you can change the note is by changing the tuning peg, and that is basically wrapping up the string and pulling it tighter. So by changing the tension, you can actually change the wave speed. A tighter string allows the wave to travel faster down that string, which means there are two actual ways that you can increase the frequency in a string. You could increase that tension, or you could change what the effective length of the string is by putting your finger on a certain fret. So you can decrease the length, that will increase the tension or increase the frequency. You could also increase the tension, that would do the same. We are going to focus primarily on the length because the tension is a little harder to define exactly how the tension is going to impact the wave speed, but the length is a little bit easier for us to measure. So if we're to look at an actual picture, this is where it gets a little bit more complicated. You see a node on each end, and that can create a standing wave. If you were to watch the actual amplitude and movement of the string, the simplest way that it can move is basically oscillating kind of like a jump rope, back and forth between two positions where it doesn't move on the nodes. Again, how we count the number of wavelengths is we look at just one side of this because it's oscillating back and forth. That is not a complete wave. That's actually only half of a wave. So we're going to say that L, the length of the string, is equal to half of the wavelength for that wave. If we go to the next most complex standing wave, you could actually get two standing waves in there. Two standing waves is the same as just one wavelength. Looking at just the green part, it goes up and then down and then back. That's one wavelength. My next most complex is three standing waves. Three standing waves, 3 over 2, is 3 halves of a wavelength, or 1.5 complete waves that are there. Now, one of the ways that we can talk about these different positions, all of them can happen. There are ways that really good string musicians, whether it's a violinist or a guitarist, can place their finger lightly and actually encourage one of these higher standing waves to form. So it's not the simplest one. You can do some terminology here and talk about these waves. This first wave, we call it the first harmonic. So it's harmonic number one. Sometimes this is also referred to as the fundamental frequency. It is the simplest waveform and usually the loudest wave that you hear. If we go up one, that is now the second harmonic, followed by the third harmonic. You will notice here it actually follows the numerator in this fraction. So 1/2 becomes the one harmonic. 2 halves, or one, is the second harmonic, and 3 halves is the third harmonic. You can also have a wave form in an open pipe system. An open pipe resonance is something like a trumpet. A trumpet, you have a vibration that's happening at the lips, so an open end on one side, followed by an open end on the other side, and you create a wave that has an antinode on both ends. What that looks like is this. This is the simplest standing wave that ends with antinodes. That, if you follow just one side, is half of a wave. It starts at the peak, ends at the trough, but doesn't go back. If I go to the next most complex standing wave, I have an antinode on both ends. One complete side looks like it starts at the peak, ends at the peak. That's one complete wavelength. And then here, you can also fit this picture. That is 3 halves, or 1.5 wavelengths. You'll notice that's actually the same stuff as before. We're going to call this first, second, and third harmonic again. So the simplest one is the first harmonic, or the fundamental frequency. Now, if these are the same length instrument, you'll notice that something is changing about that wavelength. Bugle is a trumpet without any valves. The only way a instrumentalist playing a bugle can actually change the notes is by changing the speed of the buzz of their lips, and they can get different frequencies to oscillate in that system. But it's not every possible note. There are some discrete notes that can be played because what's happening inside is mapping to different standing wave waveforms, the simplest being the lowest note, followed by the next highest, the next highest, the next highest. Because as you are shrinking your wavelength, you are making more waves per second fitting in there with that speed of sound, causing a higher pitch. So any song that can be played on a bugle, you'll notice only contains these notes that are in that scale, um, including the most famous bugle song, Taps. Dun 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 dun. It is jumping from harmonic to harmonic because those are the only notes that are able to be played. There's another type of instrument that resonates air. This is called a closed pipe resonator. If you've ever taken a bottle and blown over the top of a bottle, this is a closed pipe system. It is not closed on both sides. It's closed on the bottom where the water is, and then open on the top where you're blowing across. In this system, where the water is, that closed end has to be a node, and then the open end is an antinode. So antinode, just like on the open, but now we have a node on the other side. The simplest standing wave that meets this configuration, it looks like this. There's a really simple wave, and you'll notice that's not very much of a wave. It goes from the equilibrium up to the maximum point. If we went back down to the equilibrium, like we saw before, that's half a standing wave. So this is actually a quarter of a wavelength. The next simplest wave looks like this. That is 3/4 of a wavelength. The next simplest wave looks like this, and that is 5/4 of a wavelength. Here, we're going to name the harmonics in a slightly different fashion. We're going to call this, again, the first harmonic. That's the same as the other ones. It is the fundamental frequency, a quarter of a wavelength. But then our numerator is changing, is jumping in different ways. So we're going to call this the third harmonic and the fifth harmonic. That's going to be kind of weird and awkward, but that is the official terminology when we refer to these harmonics as these higher frequencies that are being played. Again, it's mapping to that numerator in the equation. So I do not expect anybody to memorize all of those pictures. You can memorize these end conditions, though. You can remember that a closed pipe, that's closed on one end, open on the other, is a node on the closed, antinode on the open. Open pipe, open on both sides, is antinode on both sides. And a string, because you have it fixed on both ends, has to be a node on both sides. And from that, you can draw these pictures. Um, these pictures are a standing wave, just part of that standing wave to match these end conditions, getting more and more complex as you go. And if you know those pictures, you can look at one side and figure out how many wavelengths in the length, and then use some equations to find the rest. So as a reminder, high-pitched sounds have high frequencies, low-pitched sounds have low frequencies. We saw how a trumpet or a bugle can increase the frequency by cramming more wavelengths in the same length. There's other ways that you can change the frequency. A pipe organ is basically always playing at the fundamental frequency. That's the first harmonic. So unlike a bugle that changes the harmonic to change the note, a pipe organ changes the length of the pipe. And then each pipe has a different wavelength, even though it's fitting the same number of wavelengths. Because the length of the pipe is changing, you are stretching out that wave. And as that wave gets stretched out, its frequency goes down because its wavelength is getting longer. So let's try a problem using this idea. An open organ pipe, so that means it's open on both ends, is 2.1 meters long, and the speed of sound in the pipe is about 341 meters per second. What is the fundamental frequency of the pipe? So fundamental frequency in this case is the first harmonic. That is the simplest waveform that can fit. We know that this is the wave speed equation. V is equal to F times lambda. Rearranged for F, F is going to be what we're solving for, and V here is 341. Wavelength, I don't know until I see a picture. This is my situation. I've got an open organ pipe. Open is antinode on antinode. It's the fundamental frequency, so it's the simplest picture that fits that end condition. If I look at this picture, looking just at one side, if the pipe is 2.1 meters long, that is half a wavelength. So this is not a complete wavelength. It starts at the top, ends at the bottom, but does not come back up to the peak. So that half a wavelength, if I know that the length is 2.1, I can solve that the wavelength is 2 times the length. 2 times 2.1 is 4.2 meters is the wavelength. Now I have V and I have lambda. We can solve for the frequency. 341 divided by 4.2 is 81.2 hertz. That's a very low note, but it makes sense. It's being played by a very large organ pipe. So again, we took this wave speed equation, figured out what we know. This length is not a wavelength, but it can be used to find a wavelength if I know what the picture looks like. Let's try the same thing for a string. The note produced on a violin string of length 40 centimeters produces a wave speed of 250 meters per second. That is not the speed of sound through the air. That's the speed of sound, speed of the wave traveling through the string itself, which again can be changed based on the tension. What is the first harmonic of this note? So yet again, we're trying to find F. We know what V is, but we don't know what the wavelength is. We do have a picture that we can draw. This is a fundamental frequency, the first harmonic of this string. So a string is note on both sides. Picture looks like this. That 40 centimeters is half of a wavelength. So just like we saw with the open pipe, half a wavelength means that the wavelength is 2 times L. 2 times zero point 0.4, 40 centimeters into meters, is zero point 0.8 meters. If I know the speed and I know the wavelength, I can find the frequency as speed over wavelength. 250 over zero point 0.8 is 312.5 hertz. All right, the last situation that I want to look at is you can sometimes change the resonance space to make a note resonate louder. A common example of this is taking a tuning fork and holding it on the open end of a pipe and then changing the pipe's effective length by moving it up and down in a column of water. When you do that, you create a standing wave with that column of water acting as a closed end of the pipe. So we have an open side on one side, closed on the other. We are going to move that resonant space until it matches this waveform of my standing wave. So I see that there is a standing wave that would form here with an antinode and node. If I kept going, I would actually find another standing wave here, and then there would be a third continuing beyond, because this tuning fork has a set frequency. A set frequency has a set wavelength. A set wavelength is going to result in a set resonance space that we can actually calculate. So you find an unmarked tuning fork in your collection. You notice that the smallest length for resonance is 12 centimeters. If the speed of sound is 345 meters per second, what is the tuning fork frequency? All right, so we know a couple things here. We know that this is the first picture, that the smallest length that's going to be formed. We know that frequency is wave speed over wavelength, and that this is essentially the picture that's happening in here. Closed on one end, open on the other, node, antinode. The length of that pipe is a quarter of the wavelength. That is a quarter of a wavelength that's resonating in that space. If I plug in or I rearrange to solve for the wavelength, that's 4 times the length of this because that's only a quarter of a wave. This length is 12 centimeters. So 0.12 centimeters times 4 gives me a wavelength of 0.48. That is the total wavelength if I kept going because I only see a quarter of it. Plug that in with the speed of sound, and I find that the frequency is about 718.75 hertz. I could keep going and find a second resonant position. This is the same wavelength. Now I know that this second resonant position is effectively the third harmonic, so it's 3/4 of a wavelength. It's the same wavelength, so 3/4 of that wavelength will give me a new length, which is now 0.36. Another way to think about it is it's essentially 3 times what it was before. It was 12 centimeters, now it's 36 centimeters. Okay, so in those few examples, you get a taste of how these instruments form standing waves. It should be identify and label a node and antinode on a standing wave diagram. You should be able to describe the end conditions, both nodes and antinodes, for open pipes, open on both sides, closed pipes, which we're going to call open on one side and closed on the other, not closed on both, and then a vibrating string, which is a node on both sides. And you should also be able to calculate the wavelength or instrument length of a standing wave for different harmonics. So what we were doing there, taking that picture, turning the length of the instrument into a wavelength, and then using that wavelength to solve for something else like the frequency of the wave.